main research interest is in optimal transport theory, and today I want to talk about a project I've really enjoyed. So it started out a very applied project and an application of optimal transport in industry, in the steel industry. But this very applied project has actually led to some nice new mathematics. Well, it's working. Let's see. Well, I can do it here instead. I think it's frozen a minute. Okay, now it's working. Yeah. Okay, so this is works as a research program. It started around 2017, 2018. Initially, it just me and Pete Koch from Tata Steel Research and Development here in the Netherlands. So Tata Steel is, I guess, one of the largest steel producers in Europe, and has its big R&D centre in the Netherlands. And over time, though, its program spread to include lots of other people. And we're mainly focusing on two papers today. So these ones in red at the bottom. So a published paper from 2025, and then a preprint as well that will come out in, well, maybe this year, maybe next year. Okay. So first, a bit of background in geometry. So I'm going to be talking about some convex partitions, so tessellations by convex polygons, convex polyhedra, and a special type of partition called the Gallouët tessellation, which is similar to a Voronoi diagram, if any of you know Voronoi tessellation. So I'll give you a couple of alternative definitions. The first one, define them in terms of convex functions. So let phi, from as a function on Rd into R, be a piecewise affine convex function. So it's piecewise affine, so its gradient, we're just going to assume it takes on finitely many values. So it's a piecewise affine, its gradient is piecewise constant, and it takes the constant yi on the cell Li. And since phi is convex, these cells are convex as well. And the collection of cells Li, where the gradient is constant, that they form a partition of Rd by convex polytopes, so convex polygons in 2D, convex polyhedra in 3D. And this is known as the Gallouët tessellation or a power diagram, and it includes Voronoi diagrams, if you're familiar with them. It's not all possible partitions by convex polygons, but it's a lot of them. In particular, in R3 and higher, it includes all normal tessellations, kind of all nice tessellations. Okay, this is one definition, and then another one that's kind of more connected to optimal transport is the following. So, alternatively, define Gallouët tessellations in terms of they're generated by weighted points. So I've got n points yi in Rd, and every point has a real value weight with it, psi I. We've got n weighted points, and then these generate Gallouët tessellations that's partitioned by convex polytopes according to these inequalities just here. It looks a bit funny, but I've written it in such a way that you can really see this is a convex polytope. So this is the equation of a half space. If there was a half space, this would be the normal to the boundary, and this tells you that essentially the distance of the boundary to the origin. And this is for all J's. We're intersecting a bunch of half spaces or half planes in 2D. If you intersect a finite number of half planes, you'll get a convex polygon. And so that's one way of defining them. And so yeah, the Gallouët cells again, the convex polygon that's in 2D and convex polyhedra in 3D. And to make it look more like optimal transport still, you can rewrite these inequalities as follows. So the Gallouët cell, it's all the points x and Rd satisfying this inequality for all j. Here we see the Euclidean distance squared, and this will come up in the two Wasserstein distance. Yeah, the formula is not so important. The important thing is their convex polytopes. So these will be one of the main objects of study in this talk. So before I talk about the next tool, are there any questions about the Gallouët tessellations? Is everyone happy with the definition? Yeah. Okay, so the Gallouët tessellations is one tool. Another tool we'll need is some optimal transport theory. And in particular, so my favourite type of transport is called semi-discrete optimal transport. So I like it a lot, it's very geometrical, as we'll see. So what do I mean by semi-discrete transport? Here I mean optimal transport where the source measure is an absolutely continuous probability measure, so rho here, and the target measure is discrete. So it's called semi-discrete. So if you like, we've got a continuous source measure and a discrete target measure, semi-discrete. So we're transporting rho to nu, and you can imagine the source measure here is like a pile of sand, and rho tells you the height of the sand, and the target measure nu, it's like you have a load of buckets where we want to transport the sand. So the buckets are located at positions yi, and they have capacity vi, and we're not creating or destroying mass, we're really transporting it. So these are both probability measures, so the capacities of the buckets have to add up to the volume of the sand. And yeah, so this has to do, and there's only finitely many places the sand can go. We've got finitely many buckets, and that means that, and then we want to move the sand to the buckets in an optimal way, so with least effort. And since there's only finitely many places we can go, the transport map will partition the domain. So we'll put it into regions. There'll be some region which goes to this bucket, another region which goes to this bucket. And so this is the link with geometry. Is the transport map will create a partition. Okay, so this is the definition. This is a 2 Wasserstein distance, but I'm writing it down just for the special case of an absolutely continuous source measure and a discrete target measure. So it might look a bit different from if someone who's seen transport before. It may look a little bit different than the definition you've seen before. But you can write it as an optimal partitioning problem. So in this picture, the red dots are the locations of the Dirac masses. And we want to partition our domain up into, so there should be 1 cell per Dirac mass, and there's a capacity constraint that so the volume. Say this cell is going to be transported here. The volume of this cell with respect to rho should equal the volume with respect to the target measure. So the volume of this cell equals the capacity of this bucket. So that's the admissible partitions. And what we're trying to minimize is this essentially L2 distance. So if you're in region UI, so X is going to be transported to YI. So you pay the distance squared, because it's the 2 Wasserstein distance. Distance squared for transporting X to YI. This is the amount of mass we're transporting, and then you add it up over the whole domain. So it's the standard 2 Wasserstein cost, but specialized to the semi-discrete setting. And so you can minimize all possible partitions, they all Borel partitions, but it turns out the optimal partition is in fact a Legere tessellation. And so why is that? Well, so if you're familiar with optimal transport, there's Brenier's theorem, which says the optimal transport map is the gradient of a convex function. So the map's the gradient of a convex function, but we can only transport to a finite number of places, so it's going to be a piecewise affine convex function, because the gradient, it can only take on these constant values. So the optimal transform map is a piecewise affine convex function, and in particular, that means the cells are going to be convex, they're going to be a Legere tessellation. So this goes back to my original definition of Legere tessellation. And what do I mean to say it's a Legere tessellation? So in particular, you can prove there exists weight. So for every Dirac mass, there exists a weight, a real valued weight, such that the optimal partition UI is the Legere tessellation generated by these weighted points. So the seeds yi, they're coming from the support of the target measure, and well, you have to choose the weights appropriately so that it's an admissible partition. Essentially, it allows you to slide around the boundaries of these cells so they satisfy the volume constraint. And moreover, so this is just saying they exist, you can actually compute them by solving a nice convex optimization problem. So if you're familiar with transport, I use this notation because these are the optimal dual potential psi evaluated at yi. So psi I would be the dual potential psi evaluated at yi.
Really dumb question, sorry to interrupt you. Is that unique?
The partition is unique. The weights aren't unique, you can always add a constant to them, but the partition is, yes, unique. Yeah, there's a unique transport map.
Right, and you go back the other way, so taking the tessellation and define an optimal transport problem that matches it.
So if you give me a Legere tessellation, say, yeah, you can find you can define the target measure in such a way that, so yeah, you take the target measure. If you give me a Legere tessellation, So that comes with a set of weighted points that generate it. The seeds would be your give you the support of the target measure, and these VI would be, you take these to be the mass of the Laguerre cells. You define VI to be rho of UI.
Sorry to interrupt, thank you.
No, that's good. Thanks for your questions. Was that what you're asking? Yeah, cool. Thanks. Yeah, you want to speed that questions? Yeah, that's really good. Are there any other questions about the optimal transport or the Laguerre situation?
So just one question. The constraint is that you have your points living in the same domain as the rho function.
So actually here I've drawn a square, but it's more like we're working in all of RD, but rho is going to be I didn't write it down. So it's absolutely continuous with finite second moments. So typically in applications, the steel industry application rho would be just the Lebesgue measure on some given domain. So in this case, it's the Lebesgue measure on the square. But in principle, it's all of RD, and rho is just absolutely continuous with finite second moments on RD. So it's not really a domain. I know from the way I've drawn it, it looks like there is, and kind of that's what I think in my head. Because normally in applications, rho is it's just going to be the volume measure, just the Lebesgue measure on some rectangular domain.
Okay.
So all my pictures actually will be in a box, even though actually it's really always an RD.
No, it's okay, but it's RD, right?
Yeah.
To extend to Wasserstein P.
Yeah, Wasserstein P, yeah, so the result is a similar theorem for Wasserstein P, and then the optimal partition would be what you call a P Laguerre tessellation, and the only difference would be you'd have a P Laguerre tessellation where you replace this 2 by a P. So if it's the P Wasserstein, so it's the 1 Wasserstein, you'd have the power 1, and that's something known as an Apollonius diagram. And in general, if it's P Wasserstein, you'd have a power P here. The problem is then your cells are not convex, and the computations are much harder. But in principle, and the result's true for any power P. Any other questions about the transport of the Laguerre? Yeah.
Can psi be found as a function of the VI? Like, is there?
Yes, as you can find these by, so there's not an explicit formula, but you can solve the dual optimal transport problem. So that's maximizing the concave function. And it's a finite dimensional concave maximization problem, unconstrained. So it's very tractable, and you can solve that. So even with like people have done it with, and I've done it typically with maybe 10 to the 5 particles. People have done it with millions and billions of particles. So it's there's not a formula, but there's kind of very good software for doing it. For the 2 Wasserstein, it gets more complicated with a general P. So the idea is so what's the application in the steel industry? So I want to mention this briefly. So I want to tell you what this picture is. This is it's kind of a tessellation that arises if you zoom in on a bit of steel or a bit of metal. And what you're seeing here, so a quick crash course on the microstructure of steel. So you may know from school that atoms in metals tend to form lattices, so regular periodic structures. And that's not entirely true. So it's true locally that they form a lattice, but the orientation of the lattice varies throughout the material. So what you actually see are things called grains. So this is a 2D cartoon. We've got a square lattice here. So these are all square lattices. But of course, a square lattice, you can rotate it, it's still a square lattice. So we've got the square lattice, and we have like a piecewise constant orientation function. So here we've got one orientation, here we've got another, here we've got another. And these regions of constant orientation are called grains. So this is a metal. And yeah, so these, what look like convex polygons, these are all grains. You have a different lattice orientation. And they do look very nice, and this is an exceptionally nice picture. But so sometimes they do really resemble convex polyhedra. And if you had like highly idealized cooling conditions where you had a molten metal, it starts solidifying from a few points at exactly the same time, and it's solidified exactly the same rate in every direction. Then you'd end up with actually a Bourne diagram, to a special type of Laguerre tessellation. So you wouldn't get convex polyhedra. Of course, real life's more complicated, but that's just to give you an idea why these look like polygons. This is 30 microns, so you won't see this with the naked eye, but I guarantee you have seen grains as you've been walking around town. So you'll see these sort of patterns in railings and lampposts, and so these different shades of grey here correspond to grains. So the different shade of the grey or the silver, each one of these is a different grain. This is not steel, this is in the zinc coatings, like galvanized steel. So you've definitely seen them, and now you know what they are. You'll see them everywhere. Okay, so you see these, if you look then at this sort of galvanized steel, or if you look at the microstructure steel, you start to see partitions, tessellations. So that's the link with how I started the talk. And here's another. So this is a picture that my collaborators at Tata Steel made. So this is what's called an electron backscatter diffraction scan, EBSD scan of a steel. So every color here corresponds to a different lattice orientation. I think in this picture, the grains are kind of elongated up down a little bit, and that's due to the rolling process when they make the steel. Right? They do lots of hot rolling, cold rolling. So that's this is what 50 microns here. So there's actually a huge engineering literature on using Laguerre tessellations to model the microstructure of steel, and they use it for a couple of things. So one, which I'm not really going to talk about today, is generating synthetic microstructures, so statistically representative artificial microstructures that they can use for, say, computational mechanics, for computational homogenization. So we've actually just released, we have this kind of a library and a graphical user interface for doing this. So this is with an impact engineer in Heriot-Watt and a collaborator in Glasgow. But there's a massive literature where people are doing this to model the microstructure of steel. So we're hoping that maybe one day this will turn into an impact case study, but it's quite tricky, especially as our collaborators are still in R&D, Tata Steel, but it's research and development. So getting the evidence that you've actually, made a difference. I'm not sure if we'll have it for the next draft, but who knows. So that's one application. But today I'm going to be talking about, I guess since this is sort of the statistics seminar, a kind of a regression problem, a fitting problem. There's also a large literature where engineers try to fit Laguerre tessellations to images of metals. So for example, this is another EBSD image of a metal. So the colors correspond to a different lattice orientation, and they try and fit Laguerre tessellations to it. So then I'm going to tell you more later how this picture is made. So obviously the Laguerre cells are convex, and these aren't all convex. So some cells it does pretty well, and some cells it doesn't do so well. And you could use fancier tessellations, and we do that as well. But often, so in this case, if you really know every pixel which grain it belongs to, you can do something like logistic regression. But often you have incomplete data, so you don't actually have this image. If it's a large 3D sample, and you have to do X-ray diffraction, then you don't actually have this picture to start with. You don't know for every voxel what grain it belongs to. Sometimes they'll only know the volumes of the grains and the barycentres, the centres of mass. And so you want to fit Laguerre tessellation to these two bits of information, the volumes of the cells and the barycentres. And that's what I'm going to be focused on, so kind of regression with incomplete data. So in particular, this is it's kind of looking ahead. So here what you're seeing is there's two sets of red. So each cell here has the same area as the cell here, but the tolerance we chose, that comes from optimal transport. The areas you can do fine. And the red dots are the actual barycentres or centroids of the cells, and the blue dots are the target barycentres, so the barycentres of these cells. Sometimes they're kind of indistinguishable, but sometimes you can definitely see a difference. So what we're trying to fit here is kind of do essentially least squares fit between the true barycentres and this tessellation and the target barycentres. So I want to talk a bit about that and kind of the mathematical problems that it's given rise to. That's kind of the motivation where we were coming from. So maybe now I can state the problems rigorously, and then maybe see if you have more questions. Okay. So yes, the point is, we had this very applied problem. Initially, we were just using standard tools from optimal transport, but actually it's given rise to some nice pure questions. So I want to kind of list these pure questions now. So these questions were inspired by the work with Type Steele. So throughout the rest of the talk, rho is going to be a fixed, absolutely continuous probability measure with finite and second moments. Typically, it will just be, I mean, applications, it's just the volume of a, say, a rectangular domain in 2D or a cuboid in 3D. And given a subset, so just a fixed notation, if you're given a subset of ID, we define U, so the barycentre of U, or the centroid of U, or the centre of mass of U, whatever you want to call it. So this is the usual definition of centre of mass. So it's the first moment of U with respect to rho, normalised by the volume of U. Well, I often refer to rho as volume, just for simplicity. So this is the usual definition of barycentre. Okay, so with this notation, the questions we had. So if someone gives you this discrete measure, so they give you a bunch of target volumes and target barycentres, these are points in RD. Does there exist a Legare tessellation whose cells have these volumes and these barycentres? So can you find a Legare tessellation that has cells of volume BI, volume with respect to rho, and barycentres BI? Again, barycentres with respect to rho. So that's one question. Under what conditions on the data does there exist a Legare tessellation? And then if it exists, is it unique? And then if it's unique, can we actually reconstruct it? So if someone, they just tell you the volumes and the barycentres of the cells, can you then tell them what the tessellation is? And finally, kind of going back to the engineering problem, so normally with the data coming from engineering, there doesn't exist the Legare tessellation that has exactly the right barycentres, and instead we want sort of a best fit problem. So can you find a tessellation where the cells have the right volumes and approximately the correct barycentres? So these are the questions I want to discuss. I'm not sure if we'll get as far as number 4. But are there any questions about the questions? Does this again make sense?
Oh, yeah.
Okay, so I'm going to answer them, although not in this order. I'm going to answer them in kind of a historical order, meaning the order we solved them, rather than what's maybe the more natural order presented here. So actually, the first question we answered, the existence ones turns out to be quite hard. So actually, the first one is uniqueness. This is a theorem. So yeah, you're given this discrete measure, you're given target volumes and barycentres. And now suppose that does exist a Legare tessellation where the cells have your desired volumes of barycentres, then the tessellation is unique. So in other words, Legare tessellation is uniquely determined by the volumes and barycentres of its cells. So say you take this tessellation, and if I tell you the areas of all these cells, and I tell you where the centres of mass are, then you can't find any other Legare tessellation where the cells have the same areas and the same centre of mass. In fact, the results are actually stronger than what I've written. If you have any tessellation, not just the Legare tessellation, with the same volumes and barycentres, then it has to be the Legare tessellation. So it's a lot of information actually. So you might imagine that you could maybe move the boundaries a bit and kind of keep the areas the same and keep the barycentres the same, but you can't. So it's unique. And this follows, it's actually, I was kind of surprised it wasn't known in the literature already, but it doesn't seem like it was. And it follows just from uniqueness of transform maps in the end. So kind of a standard result in optimal transport. Yes, they are unique. So that means then it makes sense to ask question 3, which is, can we recover them? So how can you reconstruct the Legare tessellation from only the volumes of the barycentres of its cells? Yeah, so again, you tell me the areas of these cells, you tell me where these points are, the centre of mass of each cell, can I give you better tessellation? And the answer is yes. And in fact, it's a convex optimization problem. I just want to show you the problem. So just a bit of notation. So I'm letting Y, so capital Y is n points in RD. This is the collection of seeds that will generate a Legare tessellation. and V will be the target volumes. So V is a vector in Rn of positive entries, so Vi all positive and sum to 1. This is the point in the probability simplex. And the semi-discrete transport tells us, repeating what we had earlier, you can always find real valued weights, such that if you take the Legare tessellation using these seeds and these weights, which that's defined by this formula, then the cells have the volumes Vi. So if you just give me the volumes, I can always find the Legare tessellation that has cells of the right volume. No barycentres here for that. And that's always possible. So then, oh yeah, I'm going to denote just for the next slide. So LIYB, this will denote the Legare tessellation. So this is Li is the ith cell in the Legare tessellation, where the seeds Y and the cells have volume Vi. You can parameterize them in terms of seeds and weights, or you can parameterize them in terms of seeds and volumes, thanks to the semi-discrete transport. So now I can tell you the theorem. Okay, so this is the reconstruction theorem. So you're given, as usual, a discrete measure, some target volumes and target barycentres, and suppose there is a Legare tessellation, so there are some seeds, so that the Legare tessellation, if you construct the Legare tessellation with seeds Y and volumes Vi, then these have the right volumes of barycentres. So suppose it exists, can you actually recover it? And the answer is yes. And so the seeds, they maximize a concave function. Actually, the formula doesn't really matter. But the point is, the reconstruction problem is a convex optimization problem. So you maximize, there's unconstrained maximizing a concave function, and that will solve the reconstruction problem for you. And so this would, I don't want to talk about the formula. This is a 2 Wasserstein distance squared, and this is a quadratic function of the seeds. It's kind of like the difference between Wasserstein costs. And so the important thing is the reconstruction problem. It's a nice convex optimization problem. There's one caveat though. So the caveat is, so H is maximized by the solution of the reconstruction problem, but it's actually also maximized by any constant vector where you put all the seeds in the same place. So in principle, if you actually solve this numerically, it could end up giving you the constant vector. In practice, it doesn't seem to. It always seems to work. But yeah, for honesty, that caveat should be there. And I don't want to talk about the proof really, but just to say, I mean, it's quite straightforward. You just compute the gradient of H. You've got to be a bit careful differentiating the Wasserstein cost, but you compute the gradient. If you differentiate H with respect to the ith seed, you get Vi times Bi minus the barycentre of the ith cell. So if you were maximizing point, the gradient vanishes. If this vanishes, that means the barycentre of the ith cell is Bi, and so you've reconstructed the tessellation. And also, so H is not C1 on the whole of RD, RDN. It's C1 provided your seeds are distinct. So it's not actually, it's not a smooth optimization problem. So it's not C1 everywhere. So it's still some slight difficulties. It's a non-smooth convex optimization problem. But it can be solved, and it seems to work well. Are there any questions about that? Okay. So what did we talk about? We spoke about uniqueness and reconstruction. So now I want to talk about existence. So conditions on the data, the BI and the BI, so that there actually exists the Legare tessellation with cells of the given volumes in barycentres. And so this, so with my collaborator in Scotland, we were stuck on this, and the solution came from a sort of a random conversation when I was in Paris in 2024.
Yeah. Can I ask you a question? So the concave function H here?
Yeah.
So is there some connection with this and sort of things like entropic optimal transport, where you have some kind of, regularization?
So this, maybe not within
And not, just the general idea, you have some time involving transport distance and then some other times like what you've got here.
Yeah, that's true. So in the yes, you've got the transport term and another term here. It's
They're different, I think.
yeah, I mean actually it comes up somehow it comes up in kind of gradient flows and JKO schemes.
Okay.
So that's actually a connection which helps to solve the existence problem. But it's right. I mean, in entropy, you'd have a Wasserstein term and then another term penalising the marginal discrepancy.
Yeah.
But here it's fully balanced transport. But yeah, so there is a connection. The surprising connection is this function h, almost exactly the same function, comes up if you look at higher order JKO schemes for gradient flows. So it's known, so for example, the heat equation is the Wasserstein gradient flow of entropy, and in general, a lot of nonlinear non-local diffusion equations can be recast as Wasserstein gradient flows. And that was really important initially for kind of theoretical, like proving existence, stability. But people have recently started using it as a numerical method, so trying to use JKO scheme for numerical methods for solving diffusion equations. And if you just do JKO, that's first order in time. If you look at higher order methods, you end up maximizing functions very much like this. There's kind of this connection. So when I was in Paris, I showed this to Thomas Gallouët and Quentin Mérigot, and then Thomas said, "Yeah, this is yeah. I mean, it was working on almost exactly the same function, and this ended up helping us to solve the existence problem." So yeah, so the question we were stuck on was question 1, which if you're given your target volumes of barycentres, does the crystal get tessellation where the cells have these volumes of barycentres? And we had no idea how to do this until so these collaborators in Paris helped us. So we just need a little bit, one more definition. This is something I think people in probability might be quite familiar with it, but it was new for me. So it's the notion of convex order. So 2 probability measures, nu and rho. These are probability measures in RD, so with finite second moments. These are said to be in convex order. So nu is in convex order with rho, or nu is dominated by rho, if and only if the integral of nu against phi is less than or equal to the integral of rho against phi for all convex functions. So this is just the convex test functions. And yeah, so this is the definition of convex order. It was new to me, but it seems it's very important in what's called Martingale optimal transports and kind of robust finance, mathematical finance, and option pricing. So for proving bounds on options, it seems that it comes up here. So, so in particular, 2 measures are in convex order if and only if there is a Martingale coupling between them, Strass and Stone. But you probably know a lot more about this than me. So we'll need this notion of convex order. And since I'm in a semi-discrete setting where nu is going to be discrete and rho is absolutely continuous, I'll introduce a set essentially of measures in semi-discrete convex order. Okay, so semi-discrete convex order. So rho is absolutely continuous. Our new measure will be discrete, and then we define this set here. So Cn v rho is the collection. We've got n points in Rd, such that if you take this discrete measure, supported at these points bi, it's in convex order with rho. So it's all the points, the collection of points bi, so that the discrete measure is in convex order with rho. And we'll see some examples of points in this set very shortly. So obviously this gives you a lot of restrictions being in convex order. Like for example, I guess the support of nu has to be in the convex hull of the support of rho. And so this set here, it turns out to be, so by choosing suitable test functions phi, you can prove it's non-empty, it's compact, it's convex, crucially, and it also lives, it's like a lower dimensional set. So ambient space is Rdn, but the dimension of this set is n-1. So this set, turns out to be very, very important for us. So the definition, okay? Is there any questions? Yeah. Okay. So this is kind of our open problem. I mean, it wasn't open for very long. I mean, it's hardly a Hilbert's 10th problem. But this is what we couldn't do in our first paper, which was so I'm going to let Bn lag be rho. This denotes Bn lag denotes the set of barycentres of all possible Laguerre tessellations with cells of volume V. So in other words, Bn lag. So it's all of B, so this is the collection of n seeds in Rd, such that there exists a Laguerre tessellation with cells of volume Vi and barycentres Bi. And what we want to do is understand this set. So the existence question essentially is characterize this set. So find necessary and sufficient conditions on B to belong to this set. So there exists a Laguerre tessellation that has cells with these volumes and barycentres. We could prove some necessary conditions, but we couldn't find sufficient conditions. Does the question make sense? And so, what can we say about this set? Well, first of all, the claim, so Bn lag, this set here, it belongs into this, it's a subset of the convex set that I defined on the previous slide, which I've repeated here. So if you're in Bn lag, you're also in this set here. So B is in Bn lag, then this discrete measure will be in convex order with rho. So meaning if you integrate this against a convex function, it'll be less than or equal to the integral of this. This is kind of quick to see. Maybe this is just worth seeing. So take a point in Bn lag and take this discrete probability measure. And we want to show that nu is in convex order with rho. And so you take a convex test function, and we have to compute the integral of phi against nu. We want to show it's less than or equal to the integral of phi against rho. And so mu is a discrete measure. So if we integrate phi against nu, it's just the sum of bi, phi of bi. And then since B is in Bn lag, Bi is the barycentre of the ith Laguerre cell. So that means Bi is exactly this. Bi is the barycentre of the ith Laguerre cell. And then since phi is convex by Jensen's inequality, you can bring the phi inside the integral. And since Li is a tessellation, then here we're just integrating over all of Rd. So this is Bn lag is a subset of this convex set. But it's really a strict subset. It's not the whole set. It's not convex. And I guess you can see that because in this proof, we didn't actually use anywhere that Li is a Laguerre tessellation. If you took any tessellation with cells of volume Bi and barycentres Bi, the proof goes through. So we just use that Bi is a barycentre of Li, and in the last line we use that Li is for tessellation, and we also here use that these cells have volume Bi. But that's it. So actually, Cn includes all tessellations, not just Laguerre tessellations. The boundaries don't have to be, they can be curved. So what is this set in the end that we're trying to characterize? It's not the full convex set. It turns out it's a subset of the boundary. It's in fact the what the exposed points of the set. So the answer to our open problem was that this set of barycentres, it's the exposed points of the convex set. So what does that mean? What are the exposed points? This is a cartoon. So this is a convex set. So what would the exposed points be? So a point P of a convex set is exposed if there exists a supporting hyperplane that intersects C in the unique point P. So in this picture, what are the exposed points? So it's the boundary, some of the boundary points. It's all the points on this curved boundary, the semicircle at the top, except for the black dots. Because here you can take a supporting hyperplane that will intersect each point on this curve in a unique point. It's also these vertices here at the bottom. These are also exposed. But these dots and these straight lines, they're not exposed. So if you take a supporting hyperplane through this black dot, it's also going to include this whole line. Or if you take any point here and take a supporting hyperplane, it will include the whole line. So it's the exposed points kind of a subset of the relative boundary of the convex set. And this is exactly the set for which there exists a Laguerre tessellation with these barycentres. Yeah, so these back points, they're called extreme points, which means that they don't lie on a straight line between any 2 points in the convex set. That maybe skip the extreme points. So we could also, in fact, characterize the extreme points of our convex set, but I think I will skip that just for time. Let's get the extreme points. Because since I thought I mentioned a connection with optimal sampling, since we're in the statistics department. So it turns out if you take this convex quadratic function, maximizing this convex function on the convex x Cn, it gives you a solution of an optimal sampling problem. The sampling problem is you're given an absolutely continuous measure, and you want to find the best approximation of this absolutely continuous measure by a discrete measure, where best means with respect to the two Wasserstein costs. And what we're allowed to choose here is kind of a constrained optimal sampling, is that you don't get to choose the weights, the VI, you only get to choose where you put the direct masses. So it's the, for example, you could say if the VI were all the same 1 over n, then it'd be the optimal kind of uniform, you'd look for the optimal uniform sampler. But in general, you want the best approximation of the absolutely continuous measure by a discrete measure with respect to the two Wasserstein costs. And you can get this by maximizing this quadratic on the convex set. Of course, it's not so useful practically because we don't want to maximize convex functions, we want to minimize them. So you can write this, so it's actually the objective function would be kind of a difference of convex functions, and then you've got algorithms for minimizing difference of convex. And if you apply one of the standard algorithms, you'll just end up with Lloyd's algorithm or K-means clustering. So I don't think it actually gives you anything new in the end, but it's I thought it's kind of a nice characterization for the sampling problem. But yeah, maybe not very useful practically. So I just very briefly finished by mentioning question 4. This is kind of work in progress, but we don't have a fully satisfactory answer. This is about fitting in the Laguerre tessellation to data. So in general, unless your data is an exposed point of this convex set, there doesn't exist the Laguerre tessellation where the cells have the target barycentres. But can you find the best fit? And this is really what's important in the applications. And the idea will be to use convex optimization and projecting onto a convex set. So it will be to take a point, you project onto the convex set, and if you happen to project onto an exposed point, then you'll have a best fit. So just the projection operator. So given B in RD to be n, so n points in RD, the projection onto Cn is more or less the usual projection, but with a weighted norm. We want to find the points in Cn that is closest to B with respect to this V norm, where the norm is just weighted by the target volumes. This, it turns out, you can rewrite it as what's called a weak optimal transport problem as well. So then the algorithm is the following. So assume that the data you're given, at least it belongs to Cn, which is the case for real data. So the real data is coming from a tessellation, not a Laguerre tessellation, but the grains in the metal do form a tessellation. So this isn't really a restriction. And then you fix epsilon bigger than 0, and we rescale the barycentres, so we kind of dilate them by 1 plus epsilon, and epsilon will be small in practice. And then we're going to define a new set of seeds, which will be the seeds of the fitted tessellation as follows. What you do is, so we've got our initial point B belonging to our convex set. We've dilated it to get B epsilon, and then you project B epsilon. Back onto the set. So you're going to B epsilon, do a orthogonal projection onto our convex set, and we define Y epsilon to be the difference between B epsilon and this projection. So just here. And these seeds, under some assumptions, they actually solve the fitting problem. So yes, does it work? So the question is, so yeah, does it work? So if when you project back, you actually get an exposed point of your set, and then you will get then really Y epsilon with the seeds of the Laguerre tessellation where the cells have the right volumes, and the barycentres, they won't quite be what you wanted, the BI, but they'll be the B epsilon I. So they're not going to have the right barycentres, they're going to be dilated a little bit, but you can choose epsilon to be small. And this is a practical algorithm in the sense it's projecting onto a convex set. It is a convex optimization problem, so that will give you the seeds. And once you've got the seeds, you can find the weights by solving the optimal transport problem, which is also convex. So it's a practical algorithm. But the question is, when you project back, do you really hit an exposed point? And then we don't know if that's always the case. So what we do know, so what we can prove, so we just have a convergence guarantee for the case where actually B comes from a Legare tessellation to start with. So that's not so useful. So it's more like a reconstruction problem. Not just any Legare tessellation, but kind of a nice tessellation, something called an irreducible tessellation. That's not so important. But yeah, it's guaranteed to work. Yeah, if what you start with your data comes from a nice tessellation. But for the fitting problem, that's not the case. So actually, the case we care about, we don't know. We don't have a convergence guarantee, except it does seem to work well in practice. So this is kind of the open problem. So in practice, this is how this picture was made. This was the EDSD image I showed you earlier. This is the scan of a metal. The colours correspond to different grains. And by solving this, projecting onto the convex set, you can get a Legare tessellation, which, kind of, well, it is okay given the limitation of working with convex sets. But we don't have any convergence guarantees, so we just know from examples it seems to work, that proving that it works, or finding an algorithm that's guaranteed to work is an open problem. So I guess I'll leave you with that open problem, and thanks for your attention.
You have the optimal transport energy function.
Yeah.
Basically tries to say how do I transport this continuous distribution to the nearest bit.
Yeah.
Is there any physical motivation for why this might be the right energy function to look at?
For the metals?
Yeah.
Not really. So I mean, the process. No, it's well, the physical thing is yes, it's not really in terms of energy functional. So the point is you've got this molten metal. Yeah, if it really did start solidifying from a few points exactly the same time, then it's like a liquid metal. And then you imagine growing some spheres from a few points. If you grow them at the same speed, they're intersecting on the boundaries of RNA cells, which of RNA cells would have Legare tessellation, which comes from minimizing this energy functional. But there's no physics there. And of course, the real process of grain growth is super complicated because they there's the initial quenching, but then often they'll heat and cool, they'll do cold rolling, hot rolling, there'll be recrystallization. So the answer is basically no. It's more like what you see is, there's sometimes the cells are polygonal, and so I mean it wasn't us that introduced the idea of using Legare tessellations. There's really like massive engineering literature, so not just in the steel industry, like in mechanical engineering, in computational material science, a lot of engineers are using it. I'd say more because they look right, it's sort of nice quenching conditions, but also it's kind of a low parameter family of tessellations. In the end, they want a tessellation that has, so you can create a bunch of realistic microstructures, and Legare tessellations are low parameters, you just need the seeds and the weights. When initially people were using RNA cells, then you only need the seeds. It doesn't give you enough control over the geometry. It simply control the volumes of the cells. Then engineers started using Legare tessellations, and then more recently now people are using anisotropic Legare tessellations, where you replace the Euclidean norm with an anisotropic norm, and that also lets you control the shape of the cells. So it's more like the motivation, I'd say, was just as a way of getting a rich family of tessellations, kind of a low parameterized family, rather than any physical motivation. Yeah, but it's a good question.
Just from the picture, it looks like you might sometimes do better by having a different number of cells from what's in the original system.
That's true, yeah.
There's a way of handling that.
So we've not tried that. Yeah, you could kind of,
So let's have something awkward and it would be better split into two.
yeah, I guess you could maybe, yeah, you could start off perhaps with too many cells and then perhaps have a way of annihilating some of them, like merging them. Yeah, and then you could have, yeah, it's true, like some of them might be best represented by several smaller cells. There was one engineer at Thomas Gallouët who used what he called multi-level Voronoi diagrams, where he would essentially glue Voronoi cells together to get non-convex cells, because another limitation here is they're always convex. I guess that's the closest I've seen to what you're suggesting. But yeah, you're right, you definitely really get better bits, yeah. And you could still assign the different cells the same orientation, so they would, yeah, then kind of glue them together. But yeah, we've not tried that, that's true. I guess you need some way of, if you start out with way too many, kind of eliminating, or even a way of, yeah, nucleating new cells. It's a good suggestion.
This is not going to be a suggestion, and it's not going to be a good question, but kind of in the same vein. Looking at your EBSD diagrams, from a very applied statistical point of view, there's kind of two questions. Are you identifying grains correctly, and does the algorithm throws up this pattern? Does it throw up holes? Does it generate random? For example, can it generate randomly small grains that actually really aren't there, but because of the input data, this will cause? I've not frozen this very well, but it seems to be that everything's very nice, highly uniform, minimum, maximum, value, and
yeah, this is kind of a nice example of that where
random.
Yeah, well, the grains are quite similar in size. That needn't be the case, especially if you look at multi-phase steels, like dual-phase steels, let's say made of ferrite and martensite, then typically the martensite grains could be have a diameter that's maybe 10 or 20 times smaller. So the optimal transport will kind of let you control the volumes fine. Yeah, it's true here that it's a nice example. If you have more data, you can do much better things. Like if it's really sort of a 2D, if you really have a 2D EBSD image like we have here, say rather than some 3D X-ray diffraction, then really, if you know for every single pixel which grain you belong to, then you can do some nice classification, like logistic regression, for example, which will give a better fit in terms of if you look at the number of miscounted pixels. So here we're not trying to minimize the number of miscounted pixels, we're trying to minimize the error in the barycentres. But if you actually know where every pixel belongs to, then this is definitely not the best method. Then you can do some sort of, yeah, it's essentially a classification algorithm like logistic regression, where you really try and minimize the number of misassigned pixels. So yeah, I'd say, yeah, you definitely shouldn't do this. This is really for incomplete data. And if you have more data, you can do better. Still within the limits of the grains are always convex here, but actually they use high order diagrams. So we have some work on these anisotropic diagrams where the boundaries are actually quadratic, and then you can do much better in terms of the number of misassigned pixels, or you can even actually go to any degree you want, and at some point it gets too expensive. But I'm not quite sure if that answers your question.
No, it wasn't a decent question, but it looks very nice. I'm sure the reality is much noisier.
Yeah. This is a very nice example. That's true. Yeah. No, the reality is pretty. I guess I think also the picture I showed earlier was quite nice actually. This was also a single phase where the grains were, I think, similar in size. Yeah, I should have put a picture of a multi-phase. This one, there was well, you see some, yeah, I guess there are some small ones, but and I didn't have a picture of it, it's this one, unfortunately. Yeah, reality is very complicated, definitely. Dual phase or even, yeah, multi-phase steel. But the engineers seem to go about it.
I guess I had a question about how the fits are eventually used. Like, Because I think that answers also like how to solve the problem, because you usually need more structure in your answer. Because otherwise it seems more like a image segmentation problem. I think there are multiple algorithms.
Yeah, definitely. No, so it's used in for computational mechanics. So if they can't get a good scan, they want to reconstruct it. So it's inside Liggett tessellation, and then they want to do computational homogenization. So for every grain, they'll assign some material properties like elasticity properties, plasticity properties, and then they'll perform some sort of tests like stress strain tests or shearing tests. And they want to know how the microstructure influences the macroscopic properties. That's kind of the goal at the end of the day. And they also do things like grain growth as well. So it could be they've got lots of pictures, different snapshots in time that they want to interpolate in between. But at the end of the day, I'd say it's about developing new alloys and about understanding how the microstructure affects the macroscopic response. And it has a huge effect. Like even, say you've got a dual phase steel that's made of two types of steel, like ferrite, which is high carbon, and martensite, ferrite, which is low carbon, and martensite, which is high carbon. The volume fraction is important, but it's not just the volume of each phase, it's really the grain structure, how they mix together. So if you have lots of small grains, you have lots of grain boundaries, and grain boundaries make a stronger material, so they act as pinning for things called dislocations in the crystal lattice, defects in the lattice. So the grain structure does have like a massive effect on the behavior of the material. So if you've got multi-phase material, it's not just the volume of the two phases. The grain size is very important, and kind of how they're arranged. And so yeah, there's a lot of engineers, not just in the industry but in academia, trying to understand the relation. Yeah, so that's the application, what they meant to do at the end of the day. It's not just our focus on kind of the imaging, but yeah.